Thank you very much for that kind introduction. Over the next 3 hours, we're going to build a recommender system. We're going to learn about how that works under the hood. We're going to develop and train a machine learning model. And then in the third hour, my colleague Neha Patel is going to take over and show how we can move from a model that works beautifully in a Jupyter notebook to actually serving a model as an API using TensorFlow Serving. So what is the problem that we are trying to solve? The problem we're trying to solve is to rank all the products. We're trying to rank the products in a number of different ways. We're trying to rank the products in a personalized way, in a way that helps users find the thing that's best for them, given the stuff that they've bought in the past. And we're also trying to rank products in relation to each other, trying to find similar products. In particular, by the end of this workshop, we'll have built a you might also like recommender system. So if you're looking at a pair of shoes at the bottom of the page, it says you might also like, and then there are 16 other pairs of shoes that you might wish to purchase instead if the product you're currently looking at is not quite what you're looking for. So there are a number of different ways to rank products. At ASOS, we've got tens of thousands, hundreds of thousands of products and tens of millions of users. And so this problem becomes quite a challenging problem to solve. And so we're going to make use of deep learning methods to try and solve this problem. So the idea is that for each customer, we're going to give a score to every product, and then we will rank the products according to those scores so that the products that have the highest score get shown first. What we're not trying to do is we're not trying to say, this is a good product for you, this is a bad product for you, because irrespective, we need to be able to recommend a number of products to every single customer. Instead, what we're going to do is we're going to train a model that can say, this product is better for you than this product, and therefore this product gets ranked first and this other product gets ranked second. So we'll train a model on historic data of user purchases, and we'll evaluate it on user purchases, and we'll know where our model is doing a good job if it naturally predicts things that users went on to go and purchase, and then we can deploy it into the real world. So the way we're going to build this model is using a method called matrix factorization. If you'd come up with this model about 10 years ago or so, Netflix would have awarded you £1 million because you would have won the Netflix prize. The way this model works is to say that for every user and for every product, we're going to come up with a list of random numbers. We're then going to multiply those numbers together and add them up. So the first number in the user, we call this list of numbers a vector. The first number of the user vector gets multiplied with the first number of the product vector. The same goes for all the other values in those vectors, and then we add that all up, and that gives us a score. And we do that for every single product. And then we've got a number of scores for all the products, which we then use to rank. And we'll know we're doing a good job if the stuff that a user purchased is ranked at the top of this ranking. So of course, the problem is that we do an absolutely terrible, terrible, terrible job at this because we just pick the numbers in the user vectors and in the product vectors randomly. So you might say, well, why did we bother doing that? What did we learn? Well, we learned one very useful piece of information. We learned where we made mistakes. We learned that there were some times where a user purchased a product, but it had a very low ranking, or times when they didn't purchase a product and it had a very high ranking. And so with this piece of information, we can go back to the user vectors, we can go back to the product vectors and make little tweaks. We can say that first number in this user vector should have been a bit bigger, and the second number in the product vector, it should have been a bit smaller. And so we make all these tweaks and tweaks and tweaks, and then we try again. Then we take the multiply and add up, and we get a new set of scores. And we still do a terrible job, but it's a bit less terrible, and we made a bit of progress. So what we do is we repeat that process again and again and again until we start to get a good performance. And that's really it. So we pick a set of random numbers for each customer and each product. We find a score for each customer product pair. We rank according to those scores, and then we tweak the customer vectors and tweak the product vectors to get a better ranking. So what have we learned? Well, we started off with random numbers, but as we made all these tweaks, over time, a user vector comes to capture the taste of the user. And over time, the product vector comes to capture the style of the product. Why does it do this? It's because if I purchase 3 things and you purchase 2 of those same things, then my user vector must be pretty similar to your user vector, because we must both have high scores for the two products that we have in common. And then naturally, you will then get a high score for the third product that I purchased and you didn't. And that is what leads to the recommendation that we then show to our customers. So in order to create a you might also like recommender, we go through this process and then we throw away all the user vectors and we're just left with product vectors. And we take the product vector for, say, this product, which is this red MAC lipstick. And we can then take the dot product, that's where we multiply and add up all the numbers. We multiply this with the product vectors for every other product in our catalog, and then rank according to how similar one product is to another. So how well does this work? Well, here is the you might also like recommendations for that MAC lipstick. It's a range of other MAC lipsticks, similarly priced, but just in a range of different shades. So let's just think about this for a second, right? We didn't pass in explicit information here. We didn't pass in the explicit information about brand. We didn't pass in information about shade. We didn't pass in information about price. We didn't even pass in information about product type. And yet naturally, this model has learned by association that the MAC lipstick that was at the top of the page is similar to these four lipsticks shown at the bottom. So we learned how to rank. We didn't learn what was good for you and what was bad for you. The original Netflix algorithm did try to do that. It tried to say what is good for you and what's bad for you by predicting what score you would give this out of 5. But Netflix has now abandoned that, and now all you can do is give a thumbs up or a thumbs down, and Netflix tries to predict what you're going to like based on the stuff, not the explicit signal you've given it as a 5-star rating, but on what you've actually done on the purchases or movie views. The vectors don't have an obvious meaning, although after training, they in some sense capture user taste. They don't have explicit meanings. The first number in a user vector is not the user's age. The second number doesn't indicate their gender. It just in some way captures the user's taste. The product vectors in some sense capture the style of the products. So this was a piece of analysis done by some colleagues of ours at Stitch Fix. And they found that they were able to figure out that the products that were similar to each other actually had human interpretable styles. So at the one end, products that were similar to each other had this kind of boho style that you see on the left. And on the right, products that were similar to each other had this kind of preppy style that we see here. So that was just something that emerged naturally from the model, emerged naturally from capturing customer actions on their website. And so naturally figuring out what products were similar to each other. Okay, so I think that's enough of the slides for the time being. I can take questions now, and then we can move straight on to the workshop proper, where we're actually going to build a recommender system that does that. I see no questions, so I will move straight on to the next part of the workshop. Like this. Okay, so you've all been sent this GitHub link, and if you don't have it in your email, you'll see that it's available in the chat. So this GitHub link contains a file that we'll walk through and write together, and it also contains some data. So if you click on this link for Google Colab and then follow the instructions after that, while that's loading, I see that there is in fact a question. Rebecca Yates asks whether the length of the vectors matter. How do you work that out? For example, should you choose vectors that are small or long? And the answer is it matters a great deal, and it's a very sensible question. But the way you figure that out is pretty much by trial and error. You try one length of vector, and then you try a different length of vector, and you see which one does better in your offline evaluation. And we'll be able to talk more about that later. Okay, so here is Google Colab. And if you go to File, Open Notebook, and click on GitHub, then you can type in ASOS/DSF 2020. And if you hit Enter, then you'll see that there's this link here to the Python notebook. And if you click on that and you give it a second, it should load for you. And so this is really just a online Python interpreter, and it's run by Google. And one of the really amazing things about this technology is that if you want to run on a GPU, you click on runtime and you click change runtime type, and you select GPU and you click save. So now we're going to be able to access the tremendous speeding up opportunities of a GPU. Okay, so obviously the first thing we need to do is to import some of the libraries we're going to use. We're going to run that anyway. And we're going to run import this data set. So let's just have a quick look at the data set that we've provided for you. So if we have a look at this training data set, so you can follow along with this part if you want, or not if you don't want to. We'll introduce TensorFlow in the next section, and you can follow along if you want to or not. But then in the section after that, we will actually start building our recommender model, and it would be best to follow along if you can. When we build that recommender model, we're going to use this data set. So this data set contains a list of customer IDs, which these are not real customer IDs, and product IDs of purchases. And so these are the purchases that we're going to try and learn from when we produce our ranking. And then we've got a validation set, which we'll use to evaluate whether or not we're doing a good job. We also have this dummy users list or array, which is a complete list of all the users in our data set. And here we've got a complete list of all the products that are available on the website. And indeed, these are real product vectors. If you go to the ASOS website, asos.com/prd/ and then you paste in one of these product ID numbers, and you hit enter, then that will take you to the website for this rather nice chevron stripe knit jumper. So I think that that's how you access the products that way. Okay, so I'm about to give what I've called the briefest introduction to TensorFlow, but I will take the opportunity to answer some questions. So David Fletcher asks if there's a way of proceeding with this workshop if you don't have Windows 10 to download Docker. Well, so the first 2 hours of this workshop, we're not going to make use of Docker at all, and we will build a recommender system purely in Google Colab. And so I think that should work for you for the first 2 hours or so. There's a way to use Docker in Mac. In fact, I've got Docker installed on my machine, and I think instructions have been sent out for that. Perhaps somebody can double check if that's been received. Yes, let me re-show how to connect to the GitHub page. So if you go to github.com/asos/dsf2020, then if you scroll down into the README section, you can click on this link to Google Colab. And once you have logged into Google Colab, you go to File, Open Notebook. And you click on GitHub just here, and you type in ASOS DSF 2020, and then you click on this link. Okay, so I think that is enough. Okay, so here we've got our data set. We've looked at our data set. We'll come back to that. First, we're going to introduce TensorFlow, and then I'll take questions again probably in about 20 minutes after we've had a chance to look at that. So at its heart, TensorFlow is about manipulating tensors, and so you may be wondering, well, what is a tensor? So you can create a tensor by typing tf.constant, and then you just type in a list of numbers like so. And if we have a look at that, this has created for us a tensor. As the word constant implies, we're not able to change any of these values. We can see that this has a shape 4 by, meaning that there are 4 values inside this tensor, and we can even see what those values are, and that those values are all integers. So if I say x equals that, I can then perform arithmetic operations on this tensor. So I could do tf.math.square. And that has now squared all the values in this tensor. Now, perhaps a more traditional way of writing this piece of code right here would have been to write a for loop, and you would for loop through each value here. Pretty much the case if you're writing TensorFlow code and you're writing for loops, that you're doing something wrong. TensorFlow takes advantage of a GPU architecture to be able to perform operations in parallel. And so if you use TensorFlow-based arithmetic functions, then it's able to perform this operation in parallel extremely quickly on the GPU architecture. And this really is the main, or one of the 2 main contributions of TensorFlow to the community. And pretty much everything else is just syntactic sugar. So here we had a one-dimensional tensor, one-dimensional because it just had a single row. But we can equally write a tensor that has 2 dimensions. So for example, you need to, in order to write a 2-dimensional tensor, you really kind of write it like it's a list of lists. So you've got this kind of double square bracket notation. So if I write 1, 2, 3 in this first set of square brackets, I put a comma and another set of square brackets, I can put 4, 5, 6. And we can see that now I've got this 2-dimensional tensor. Sometimes it's also called a matrix. So you'll see that I've just been typing integers here, and the D type here is labeled as integer, but I'm able to change the data type to say be floating point numbers by typing D type equals tf.float, float 32. And you'll see the only difference here is that we've added decimal points all over the place. So we've looked at constant tensors. There's another type of tensor as well, which is called a tf.variable. So if we look at this variable right here, I'm going to call this one x as well, and I'm also going to make this a float. If we have a look at this variable, we see that it's really exactly the same, except that it's got this type variable right here. One of the things we can do with variable types that we can't do with constant types is we can track gradients. And this really is the second and other major contribution that TensorFlow brings that most other languages don't have. And that is the ability to track gradients, the ability to track how one variable changes with respect to another. So I'm going to write out the correct way to do this, and then we'll talk about why we're almost never going to write this kind of notation ever again. So if you want to track the gradient or the slope of a variable with respect to another, you write this notation. You write with tf.gradient tape, open bracket, close bracket, as tape. And then you can say something like y equals tf.square, tf.math.square of x. Okay, so nothing has happened yet, but we can look at the value of y, and those are indeed the squared values of this tensor. So 1 becomes 1, 2 becomes 4, 3 squared is 9, etc. If we want to have a look at what the value of dy by dx is, that is to say, how does y change with respect to x, then we can define that very simply like this. We can ask the tape to give us the gradient of y with respect to x. And when we print that, we see this tensor. So does anybody remember high school differentiation or calculus enough to tell me if this is the correct answer? Well, if y is equal to x squared, then dy by dx is equal to 2 times x. So if x is equal to 1, dy by dx is equal to 2. When x is equal to 2, then y is equal to 4. So we're just doubling these numbers. And so this has allowed us to track the gradient. Now you may wonder, why is that useful? And it's useful because when we build a recommender system, we figure out what our errors are. We then need to go back to our tensor and make little tweaks. And the way we just figure out which direction to make tweaks and how big a tweak to make is by looking at the gradient, looking at how the answers that we got change relative to the data that we put into them. All that being said, I personally find this notation, the with TF gradient tape as tape notation, I find this very clumsy. And the good news is we're never going to write this notation again. TensorFlow has ways of abstracting this, and we're going to make use of all of those abstractions, so we never have to do this. Apart from anything else, as you can see here, stuff gets really fiddly really quickly, and so we're going to try and avoid falling into any traps by making use of code that has already been written for us. Okay, so we looked at single tensors, and we looked at how we could follow the gradient of tensors. Now let's look at how we can multiply tensors together. So here are some tensors that I wrote before. These are x and y. So if we just have a look, x is just this this row tensor, and y is just this this matrix. And what I can do is I can multiply these matrices together using matmul. So if I put x, if I put y comma x. No, I was right the first time. It's x comma y. I multiply them together. So what operation has happened here? So what has happened here is that I've taken the values of this tensor and I've multiplied them by the columns of the y tensor. So what do I mean by that? I mean that I've taken the first value of x, which is 1, and I've multiplied it by 1. And then I've taken the second value, which is 2, and I've multiplied it by 1. And I've taken the third value, 3, and I've multiplied it by 1. And then I've added those numbers up together to get 6. And then I repeated for the second column here. So I did 1 times 2 plus 2 times 2 plus 3 times 2, and that gives me 12. And so on for this 3's column, and so on for this 4's column. So that's matrix multiplication. And indeed, we can go further. We can also add, we can add tensors together as well. So I'm just going to copy this matrix multiplication, and then I'm going to add Z. And so you'll see here what's happened is that we've taken 6, we've added 10 to get 16, we took 12, we added 11 to get 23. This is an extremely common operation to perform in deep learning and to perform with TensorFlow. So common that in fact it's been abstracted. So let's have a quick look at that. The way that we can abstract this is by typing a tf.keras.layers.dense. Well, okay, so that was a lot of stuff we just wrote. So let's break that down a little bit. So Keras is one of the modules inside TensorFlow that's used to abstract some of this complicated logic that's easy to make a mistake on. Keras is useful for abstracting some of the logic. Layers implies that we can create a kind of a number of different operations and then pile them on top of each other. So what you saw here was we started off with an x vector, we multiplied by y, we added z, and we got as output a new vector. Well, this output vector could then be passed into another, could be then multiplied again by another matrix and have a value added to it. And so we can, in this way, we can kind of build up computation. So that's why we've got this word layers here. And dense just means that we're going to perform this specific operation. So one of the really nice things about Google Colab is that it comes up with all this documentation for you right when you start writing. Units just means, well, what is the size of the output that you're looking for? So you remember that x had 3 values in here, but the output of the multiplication had 4 values. So units is the size or the length of the output. So let's say we want 4 as our output size. Activation I'll come to in a second. Use bias just means should I add z? After performing this multiplication, should I add some kind of new tensor value? So we're going to say yes, use bias equals true. And then there's a third argument that we'll pass, which is weights. And we're going to pass in a list of weights, and the weights we're going to pass in are y and z. Okay, so we'll call this layer, we'll call this dense layer 1. So I'll give you a second to catch up. So we wrote tf.keras.layers.dense. We said the output should be of length 4. We're going to use a bias because we're going to add a z value at the end. The matrix we're going to multiply x by is going to be y, and then we're going to add z at the end. And so you can see that this works because when I pass x into this dense layer, I get the exact same output that we had before, except now some of this complicated stuff is being abstracted away. So if I copy this down and put it just here, dense layer 2, I'll define a new dense layer, which at the moment is exactly the same as the original dense layer. And we'll apply a function to the output. So that's what is meant by this word activation. So after performing this matrix multiplication and then adding this matrix, we're then going to apply a function to each value here. So I'm going to define a function just in line. So I'm going to take each value in this tensor, I'm just going to add 1 to it. And you can see the effect of that, DL2 bracket x. So now instead of 16, 23, 30, 37, I now have 17, 24, 31, 38. There are a large number of possible uses for activations, and none of them come into the work we're going to do here. So we won't talk about that again, but the documentation on these things is really pretty good. Okay, so I said that one of the implications of the word layers is that we can kind of stack some computation on top of each other. And so that's what we're going to show right now. So let's define a new dense layer called DL3. So let's take the output of a DL2. So I'll call this XB is equal to DL2 bracket X. And just so that you remember, XB was equal to 17, 24, 31, 38. If I now pass XB through this third dense layer, okay, so what had happened there? So I had this third dense layer expected to output just one value, and the weights of the matrix that we were multiplying by were 0, 1, 0, and 1. So that meant that I took 17 and I multiplied it by 0. And then I added that to 24 times 1. I added that to 31 times 0, and I added that to 38 times 1. So really, we're just doing 24 plus 38, and that gives us 62. So in this way, we can kind of chain up these operations. But it'd be really nice to have a bit more flexibility in the way that we do this. And the way we do this is we define something called a TensorFlow Keras model. And that's really just a class. So we'll call this a simple model, and it's a subclass of tf.keras.model. And so a model is really just a way of chaining these layers together to give an output. So every class has to start off with an init function. And that just takes self. And whenever you're creating a new class that is a subclass of something, the first line always has to be super. You paste in the name of the module you just defined, you type in the word self, then you put dot underscore underscore init underscore underscore. And I'm not going to lie to you, I always get this little bit of code wrong. I put them in the wrong order. So pretty much I always have to look this thing up before I write it. So we're going to define, or rather, let me just copy and paste in. Let me just copy this dense layer 2, and I'll make it an attribute of the model. And I will copy and paste this dense layer 3, and again, make it an attribute of the model. So now my model contains two things. It contains this dense layer that expects to output a 4-shaped dimension, a tensor of length 4, and then this dense layer which expects to output a dimension, a tensor of shape 1. So then I need to define a call method. So what is it that I want to happen when somebody asks my model for an output? So we define a call method like this, self, and let's say the input is going to be x. So then I can say, okay, well, the output of the second of the DL2 is DL self dot DL2 of X. And then I return the value of self.dl3 of XB. Okay, so that was a lot of typing. I think I need a capital M just there. Yep. Okay, so let's construct our model. Let's call this a simple model, and we'll create it like that. And then we'll pass into this model the X that we originally had. And you'll see that just as we chained the values above to finally get an output value of 62, here we've done all of that, but we've encapsulated it inside a class. And so now we've got just a single output of 62 right here. And one of the really nice things about operating in this way is that you have tremendous flexibility, the kind of flexibility that you have when you operate in Python. So if you want to, in addition to returning the output of a DL3, you also want to return the output of DL2, and maybe you want to do something crazy and say XB, you want to say plus 104. You can now define models in that way. And so now you see we're getting 3 vectors out of this thing. We're getting this value of 62. We're getting this intermediate value of 17, 24, 31, 38. And we're also getting those values plus 104. And the final thing to say in this section is that so far, we've always been defining weights. We've always been passing in weights like Y and Z just here. But if we don't define weights, that's OK. So here's a layer that I already defined. This output looks very cryptic unless and until you look at the weights of the layer and you see that the weights have been randomly initialized for the Y matrix, and the bias or the Z vector has all been set to 0. Okay, so that was a whistle-stop tour of TensorFlow. If you didn't follow along, it's not a big deal because we haven't actually started building our recommender model just yet. But what we will do is I'll take the time now to answer some questions, and then we can move on to defining our recommender model. Okay, so some of these questions are about getting the data into the model, but I think we'll look at that later. Does capitalization matter? Actually, it really does matter. I called a variable capital Y earlier. If I called a lowercase y, then everything would have failed miserably. So we should definitely try to be consistent in our use of capitalization. Okay, so I think there are also some questions about connecting to the Jupyter notebook. Again, if you go to File and you click Open Notebook, you type in ASOS /DSF 2020. Oh, no, I need to click on GitHub first. Type in ASOS, you can then select the DSF 2020 repository, and then you can just double click on this link. So that should be good. Okay. Okay, so I think that it's, I think I've answered most of these questions just here. One person asks, can you pass in an X that has more than one row? And the answer is typically we do not do that, but there's absolutely nothing stopping you doing that. And if you want to have complicated models where X has multiple dimensions, then you can absolutely do that. Okay, so I think that, okay, so, and I'll take one more question. So Lou asks, can you explain what 4 means in the dense part again? Yes, I can. So if I copy this bit of code just here and I type out tf.keras.layers.dense and I put open bracket, then it shows me that I've got this word units just here. And I can scroll down through this notation just here. So it says units. So it's a positive integer, which is the dimensionality of the output space. So that's exactly what we saw here. What we said was that the x that we're passing in, if we just have a look at that again, so x has 3 values inside it, but after doing this multiplication, we want to get 4 values out. So the way we do this is we have a matrix that is, I got 3 rows and 4 columns, and we multiply each column by this x tensor, and that gives us an output of 4 values. And when you initially create these tensors, you create them with just these random values, and these values have no meaning. But after you expose these values to some data, you go back and you make some tweaks to all these values, and a meaning starts to, or can be thought to, emerge. Okay. So if you haven't followed along so far, it's no big deal. But now we're going to start building our recommender model. Okay. So we said that each user was defined, and indeed each product was defined as a list of random numbers. So TensorFlow and the abstraction layer Keras gives us a way to construct that. So we write tf.keras.layers, but the layer we're going to ask for right now is called an embedding layer, and that sounds quite strange. Let me just put in numbers 5 and 8, and we'll have a look at those, what they mean in a second. And I'm going to call this embedding layer, embedding 1. Okay, so what have we actually done here? So if I take this embedding layer 1 and I pass in a value like 2, then I get out a tensor of length 8. Okay, so maybe this is looking a bit cryptic right now. So let's actually look at the weights of this layer. And it would help if I didn't have a typo. Okay, so what has happened here is that we've got a tensor that has got 5 rows in it, and each of these rows is made up of 8 values, and these 8 values have just been chosen randomly. And so what we're able to do is we're able to say, okay, if we now imagine that this whole tensor here is a list of random numbers for every user, we can say, give me the list of random numbers that specifically correspond to user number 2, and we can get back that list of numbers. And we can create another embedding layer, which is an embedding layer for products. And we can say, okay, well, I want to get a score for user X and for product Y. So give me the embedding for user X and give me the embedding for product Y. And then you can multiply these two things together in ways like we've seen before. So let's actually do that now. Let's create an embedding for our users and create an embedding for our products. So if I create this dummy user embedding, okay, so what, I'm going to say that it's equal to tf.keras.layers.embedding. Okay, so what is the input dimension? So this is really asking us, how many users do we have? So the answer is, we can just take a list, our list of dummy users. So if we just remember what our dummy users look like, we can take in this list of dummy users and we just say, okay, give me one embedding for every user. So how many dummy users do we have? And then the output dimension is just going to be, well, how many random numbers do I want for each user? So I'm going to arbitrarily choose 6 just because that's a nice tractable number. And we can do exactly the same thing for the products. So we can create a product embedding, and that's just tf.keras.layers.embedding. And we will pass in the number of products. And we'll again say that the output dimension should be 6. So I'll execute that, and then we'll just have a look quickly at what the products look like so that we remember that. So that was also a list of numbers that looked like that. So now we've got an embedding for every product and an embedding for every user. And we can now say, okay, so let me take an example user. Let's say I'll take example user number 1. Okay, so that is the embedding for that user. and I can take the product embedding for product number 99, and that gives me this list of random numbers. And then I can just multiply those things together. So before we were using this notation matmul, but I'm going to introduce a new form of notation now called tensor dot. So that's called tf dot tensor dot. And so you can see here the annotation here, it expects you to give it 2 tensors and then specify axes. So first of all, we'll pass in the user tensor and we'll pass in the product tensor. And so axes just mean which sets of numbers am I supposed to be multiplying together? So I just want to multiply, I mean, there's only one dimension here, and there's only one dimension here. There's only one row. So when I specify axes, I'm just going to say I want to multiply the rows of the first tensor, that's to say the user tensor, and the rows of the second tensor there. And so those are specified by 0 and 0. And so this gives us this number, but literally all we're doing here is we're saying, okay, I'm taking this number and I'm multiplying it by this number, and then I'm adding that to the multiple of this number with this number, and I'm repeating, add up the whole thing, and it gives us this score. And so now we would say, okay, for this user and for this product, here is the score. But that's not quite what we want. We're about halfway there. What we actually want to do is we want to be able to, for a given user, we want to be able to find the scores of a large number of products so that we can then sort the products in some kind of order. And indeed, we can score multiple products at the same time. So if I choose some example products, gosh, let me say, let's take product number 1, product number 77, product number 104, and product number 2062. I'm so sorry, that was terrible notation there. Example products is of course supposed to be a constant tensor. I can then look up the product embedding for those example products. So you see, I asked for now the embeddings for 4 products, and I get back a list of 4 embeddings. And I can then follow the same approach that I took up here. I can do the tensor dot of the dummy user embedding for user number 1, and multiply those with the product embedding of the example products. Now we have to be a little careful here, and when we specify the axes, I still just want to multiply along the row of the user, but now in my products, I've now got 2 dimensions. So if I specify 0, I'm actually going to multiply along the columns, and that's really not what I want to do. I want to multiply along this row. So I'm actually looking at the second dimension here, and so I'm going to put the number 1 just there. Example product. Okay. So what do we do just here? So we took our user vector and we took the dot product with each of these product vectors. And the result of that was a set of scores. And we can now use these scores to order these products from most suitable to our user to least suitable. So I think you'll see that this is the highest score. No, I'm sorry. This is the highest score. So we show product 104 first. Then we would show product number 1. Then we would show product 77. And finally, we would show product 2062. So we can also multiply multiple users with multiple products at the same time. And in fact, that's what we're going to do when we have to train our model, because it's going to be much quicker not to just look at each user individually, but to look at a batch of users. But you could also already see just here that stuff is, again, beginning to get a bit fiddly for us. We're having to specify the axes, and it just feels inevitable that we're going to make a mistake. And luckily, TensorFlow Keras has an abstraction that we'll use that will make that life a bit simpler. there's another problem we need to solve first, but I don't want to get too far ahead of everyone. So I'm going to take a few questions now. One person asks where the products were defined. So actually, if I scroll all the way back to the very top of the page, the first thing we did was import some libraries. The second thing we did was
Hey guys, we think that Gordon might have had an internet problem, so just bear with us. We're just trying to get him back. It could be that his computer is just over processing quite a lot of things at the moment, so just bear with us and we'll get back to you. Give us 2 minutes. Hey Gordon,
hello.
are you back with us?
I think I am back with you. I don't know what happened there. I
No,
vaguely wonder how long I was talking for before I realized that I'd lost everyone.
you're good. Only about a minute or two, so don't worry at all. I think it could just be a bit of overheating happening.
Okay. So can you see my Chrome screen again?
I can. Yeah, that looks
okay.
perfect.
So I think I was in the middle of answering a question. Is that where I got cut off?
Yeah, perfect. So there's 12 open questions. I'll leave those with you, but it looks like everything's working.
Okay.
Perfect. Thanks, Mel. Hang on. Mel's just said
So
we're talking
I
about
said that we defined the products up front when we imported this list of product data, and indeed these product ID numbers do correspond to real products that we can view on the website. So I hope that answers that question. And the embedding layer, there are two numbers here. I think this answers another question that was asked. 5 says, okay, how many products do we have, or how many users do we have? Let's imagine we have 5 users, or in fact, we don't even have to imagine. When we create an embedding layer, we say, let's create a list of random numbers for every user and a list of random numbers for every product. And then how long should that list be? Well, that list should be of length 6. And we'll find later on that we can change this number and improve our recommender model. It doesn't really matter right now which number you pick, so long as both of these numbers are the same length, so that when we multiply these numbers together, there's an equal number to be able to multiply and add up together. And then we took the dot product of a user and the dot product with this product, and that gave us a score. And when we did that for multiple products, we ended up with multiple scores, which we could use to rank. Okay. So there's a second problem we need to solve before we can start building our recommender system, and that's the following problem. So if we look at our list of dummy users, our users are defined by this string right here. When we've been asking, hey, give me a user, we said, give me user number 1, give me user number 77, but actually our users aren't specified as that. They're specified as strings. And indeed, if we look just at our products, although these are specified as numbers, these are not numbers that start at 0 and go up to some value. These are numbers that have been they don't do that. So this is product number 12 million. So I guess that means perhaps that over the course of the entire age of the website, ASOS has had more than 12 million products on it. But the point is that these are not continuous numbers. Our embedding is expecting continuous numbers that start from 0. So what we really need is some kind of a dictionary where we can look up a set of values. We can say, okay, here is user ABCXYZ, which embedding corresponds to that user. So it's not entirely obvious to me how you would do that. But if we type in to Google, TensorFlow dictionary, okay, so it looks like this person was asking the same question. So if we scroll down, we can say, okay, well, this person says the answer is something to do with a hash table. I don't really understand this answer, but let's try Googling TensorFlow hash table. Okay, so this thing here looks super scary. Raw ops, I definitely don't want to click on that. So let's click on this thing called a static hash table. And again, I don't really have time to understand all of this documentation right here, but you can see that something anyway in this example is being used like a dictionary because the person is looking up some kind of value there. So in your own time, you can learn a bit more about these static hash tables, but in fact, that's exactly what's happening. So a static hash table takes in 2 inputs. The first input it takes in is the mapping from products, from product IDs to the index into the embedding. And the second thing it takes in as input is a default number to return in case you look for a user that the static hash table has never seen before. So just to be clear what's happening here. So here we're passing in the list of product IDs. And we're passing in this list right here. And we're saying map each of these values to an integer that runs from 0 up to the total number of products. And that is going to be our product table. So if I just define that product table, I can then ask the product table, okay, so what was the index of this product? So I pass in a constant tensor with this value in it, and it tells me, I'm sorry, and so you've got to call the static hash table with the method lookup. And it tells you, okay, so this first value was in fact the first value. Or if you want to look up a different value, then it tells you where was that? That was number 29,693. Okay, so if you haven't followed any of that stuff so far, it's not a big deal because we're going to put it all together inside this simple recommender model. So I've written the vague outline of this model, and we will finish writing it together. So it's a TensorFlow model, and so it needs to be a subclass of tf.keras.model. And the first thing you always do whenever you're making a subclass is you call this super init method. Okay, so into our model, we're going to pass in the complete list of products that we're going to make recommendations from among, and the complete list of users that we're going to learn about. And we create this kind of dictionary lookup table that maps each of these users to some kind of index. And then we're going to create a user embedding, which for each index creates a list of random numbers. Now, as several people have asked, you need to think carefully about what length of random numbers, how many random numbers you want for each user and for each product. And this is so important that this is going to be something that we're going to try experimenting with later. And so we're going to change this init function to also take in the length of embedding. And we're going to place that right here when we define our user embeddings, and we're going to place it right here when we define our product embeddings. So here we're just creating an embedding for every user and an embedding for every product, and that's going to be of whatever length it is that we specify. Okay, so having constructed the model, we now need to say, okay, what's going to happen when we call the model? Well, when we call the model, we want to return scores for every product. So our call method is going to expect some inputs. And the first input we're going to expect is going to be our user. So that's going to be input 0. And the second input we're going to expect are going to be the products amongst which we need to create scores. So let's assume that we've been passed in a user and a user again, just in case we don't remember, a user looks like some kind of string like this. So we need to look up our user table to ask which index in this embedding corresponds to this user. So we get the user embedding index, and that's equal to self.dummy user table. And we need to look up that table, and we need to look up the specified user. So this is the index in the embedding. We find that by looking up this table. And we're going to do exactly the same thing with the product. So the product embedding index is equal to the product table. Well, no, we need to look up the product table. Look up the product table with this list of products that we've been passed. Okay, so now we've got the index into the embedding. Now we actually need to get the embedding. So let's get the user embedding values. And we do that just by looking up the user embedding embedding. We look up, what do we look up? Well, we look up the user embedding index. And we're going to do exactly the same thing with the products. So we're going to look up the product embedding values. And we're going to, again, just ask the product embedding for the values that were at the indexes specified by this lookup table corresponding to the products. So now we've got a list of random numbers for the user and a list of random numbers for the product. We just need to multiply those together in the dot product, and that's going to give us the scores. So we said we were messing around with axes and stuff when we were using a tensor dot, and things were getting quite out of hand quite quickly. So let's use an abstraction. So in the initializer, I'm going to create a new layer, and I'm going to call that layer the dot layer, because this is going to be the layer that performs the dot product, the mathematical operation that combines the user embedding values with the product embedding values. As I just said, this is a layer, so the way we access this is by tf.keras.layers, and this is in fact called dot. And so the only thing we need to say for dot that makes this thing a bit simpler is that we can specify the axes, and we're just going to say it's the very last set of axes for both sets of inputs. So in other words, we're taking the embedding of the product with the embedding of the user, and we're multiplying those together to get a single value as output. As you may be guessing by this stage, TensorFlow is 10% writing out your model and 90% wrestling with the shapes of tensors and making sure that you're multiplying the right axes together. And so that's why you really want to be using a Jupyter style interface or a Colab style interface, so that you can experiment and iterate your way towards a correct solution where you're multiplying the correct sets of rows together, or the correct sets of numbers together. So having created this dot product layer, the final thing we're going to do is we're going to return the dot product of these embedding value of these user embedding values and these product embedding values. Now, a rather annoying aspect of the notation here is you need to put in square brackets where you pass in the user embedding values and the product embedding values. If you don't put them in square brackets, you're going to get a horrible error later on. Okay, and that's really it. I've defined a small function here, and I'll talk through that in just a second. Let's just sanity check this model and have a look and see what happens when we pass stuff into this model. So first of all, we need to construct this simple recommender. So if we construct this simple recommender, what inputs does it take? Well, it takes in our list of dummy users, and it takes in our list of products, and we need to specify a length of the embedding. And so I'm going to say, let's choose 15. Okay, so let's call this model simple recommender 1. Okay, great. So now if we call simple recommender 1, how do we call that thing? So we just need to specify some inputs, and the inputs is going to be a list, and it's going to be a list. The first is going to be item is going to be a user, and the next is going to be a list of products. So let's just remind ourselves of the different users that are available. So I'll create a TensorFlow constant tensor for my user. And I'll take this this first user just here. And then let's remind ourselves of the products. And in fact, let's make things a bit more interesting. Let's specifically pass in several users, and we'll pass in several products for each of them. So instead of passing in a single vector for our user, I'm going to pass in a list of lists of users. So I'll take that first user, and I'll take this second user. So those are the users that I'm going to pass into the model. And so now let's pass in a list of products. So again, we create a tensor using tf.constant, and we pass in a list of lists, which is the double square bracket notation. I'm going to take the first 3 products. And so I'm going to get the scores of the first 3 products for the first user. And I'm going to get the scores of the last 3 products for the second user. Now let's see if that works. Okay, so what's happened here? So what's happened here is that for this user, we've got this list of scores. So that means that we've given the highest score to this is the highest score. So we've given the highest score to this product, followed by this product, followed by this product. So this tells us the order in which this user should be shown this list of products. Whereas this list, or as this user, we're shown this list of products, but in what order? Well, it looks to me like this is the smallest. I'm so sorry. This is the smallest value, followed by this. No. Yes, and then followed by this. Okay. So that is creating a model. So now is definitely a good time to take questions. Okay, so one person asks, do we use random numbers in this model as well? If the embedding numbers are random, how does that help with prediction? And the answer is it doesn't. When we start off with random numbers and we make predictions, we do an absolutely terrible, terrible, terrible job of performing recommendations. But we do learn one thing. If we compare the recommendations we made to historical data of what users purchased, then we can say, hey, we did a really bad job with this product and this user, but we did a really good job, surprisingly, with this user and this product. And so then we can go back through our lists of numbers, through the embedding layer, and tweak and update these numbers. So we can say, hey, you know what, actually, the user, this user, PMF, actually purchased this product. So it would be much better if this had been a higher score, not just some negative number. If it had been plus 100, that would have been much better. So then we can go back to the embedding layer for that product and back to the embedding layer for that user and make tweaks to their lists of numbers, which were initially random. And by making these tweaks, we can start to improve the performance of this model. So one person asks if the tensors we've defined are on the GPU or if they're on the CPU. So the answer is that they're on the GPU, but you know, I think that one of the nice things about working in TensorFlow is that you don't have to worry about this too much, and it takes care of a lot of those kind of decisions for you. Cyrus asks if the scores are supposed to be different. So like the scores that you are seeing in your notebook, whether the scores are different compared to my notebook. And the answer is absolutely. And the reason it's absolutely going to be different is because The list of random numbers that we created for the embedding is just that. They're random numbers. And so by chance, the list of random numbers that I get are going to be different from the list of random numbers that you get. And so in that way, the scores you get out to begin with are going to be different. After we perform some training, we're going to have some kind of convergence, and so bring those numbers together. Yes. Okay. So let's look again at what's going on with the dot product axes. So one person asked about these axes, and I mean, if you're confused about these axes things, that's completely understandable because it's very confusing, and that's why in the actual model we tried not to use these axes. So what's happening with these axes is we're trying to say, okay, 0, give me the just give me the first axis, and for this user, there is only one axis. There's just one row of data, and you can see that here. There's just 6 values, and they just all sit in a row. Whereas for this list of products, there's kind of 2 axes, right? There's the rows and the columns. The outermost axis contains a list of lists, and then the innermost axis is each of those lists. And so we don't want to multiply the user by the columns, we want to multiply the user along the rows, and so that's why we specify axes equals 1. But I'm really not going to lie to you. Like, I knew that axes, the value should be 1 here because I practiced this workshop beforehand. But when I'm writing code in real life, there's a substantial amount of, well, I know which numbers I want to multiply together, but which axis number is that? Let me try number 1. Let me try number 2. Let me try number 0. Okay, now finally I figured it out. So that's why it's really important to try and iterate through a Jupyter notebook. But also it's almost inevitable the mistake is going to creep in to this little bit of notation right here. So that's why you need to both try as you go and then take advantage of some of the abstraction that TensorFlow Keras gives you. So somebody asks a bit more about the difference between little dot, between this little dot and this big dot. So this big dot is actually something that's defined inside TensorFlow Keras, and so it's a layer, and so it gets a capital D because it has some methods that we can access. But here I'm just saying, okay, I'm just created my own version of this dot product where I'm multiplying along the last set of axes. I'm multiplying the embedding layers together. And then I call that dot product down here. Yeah, so looking at these questions, it seems that a lot of the questions are about the axes, and I guess I anticipated that. Okay. So I'm leaving this code on the screen. I see that some people were saying that they can't quite follow my typing speed, and I'll try to slow down, but there's also a chance to catch up just here. One person asks, how does the hash table know to map to the right embedding within the layer? Does this mapping emerge from the training? And the answer is, it doesn't matter. It doesn't matter because the embedding layer, every single number there was created equally randomly. And so at the beginning, the random numbers really have no meaning whatsoever, and they only have meaning when we start training. And so you've actually kind of nailed it on the head there. That it kind of emerges from the training by continually saying we're going to go to embedding layer, the first set of embedding numbers for this given user, and then we make tweaks to those numbers, then naturally those sets of numbers come to embody the taste of the user that we look up every time we interrogate that. So that's what's going on there. Okay. So I think, okay, yeah, the questions are still coming in. Okay, so I think that I've answered a lot of these questions already, and I think we'll also learn some more as we go, because at the moment this has been very abstract because we've defined a model, but we haven't actually passed any data into the model, and we'll see later how to make the model actually meaningful when we pass some data into that. So I'm going to move on to that section now. Okay. So right at the top of the notebook, we imported some data. And the data we imported looked like this. So it was a pandas data frame that mapped user IDs to products that this user purchased. And the intuition here is that we'll know our model is doing a good job when it ranks products that users purchased higher than products that users did not purchase. So the first thing I'm going to do is I'm going to say, okay, just give me the user IDs and create a constant tensor of those strings. And I'm going to do the same thing for the products that those users purchased. And then I'm going to create a TensorFlow dataset. A TensorFlow dataset is a great way of passing data into the model in a very fast and efficient way that under the hood, the good people at TensorFlow have written and optimized and thought a lot about. So the way that we construct a TensorFlow dataset is with this notation here, TensorFlow data.dataset. And we say from tensor slices, and we pass in this list of the constant tensors, the users and the products. So let's just look at what it is that looks like. So you can then iterate through the data set, and you can say, okay, first give me the first value and the second value. That's to say, give me the user and the product. And indeed, when we print the user, we get this this string corresponding to the first user, and when we print this product, we get the first product. So we want to be able to rank products so that products that the user purchased get ranked at the top, and products that the user did not purchase get ranked near the bottom. So for that, what we need to do is we need to not just look at the products that the user purchased, which is what we've got in this data set, we also need to look at the products that users did not purchase. We can see that there's a large number of possible products for us to choose from. And so what we're going to do is we're just going to randomly choose from amongst these thousands and thousands of products. And from these thousands of products, we're going to choose randomly a small number of products. And we're going to say the user did not purchase those products, although they did purchase these products. Let's rank that complete set of products together and see how often we can get the purchase product ranked number one. So to do this, we're going to have to do some random sampling. And TensorFlow has some libraries for performing that. tf.random.uniform. And so you have to specify the shape. That's just saying what is the length of the output. So I will arbitrarily say it should be just 7 values, just in a single row. The smallest value that we're going to output is going to be 0, and the largest value we're going to output is going to be the length of the products. Okay, so what am I doing that for? So what I'm saying is that I'm going to randomly pick indexes into this list, and then I'm going to interrogate this list to then pull out the products that exist at those indexes. Let's look at an example. So I say that I specify a min value of 0, max value of len products, and the data type should be, of course, 32-bit integers. So let's just look at that. So I've been given this list of 7 numbers, and these 7 numbers correspond to indexes, and they're indexes into this list of products. So if I say this is now my random negatives, so negatives meaning these are the values, these are products that the user did not purchase, and so they are in sense negative values that we hope our model is not going to predict. These are the random negative indexes. That's not how you spell indexes. Let's look at the value of random negative indexes. And then we need to figure out how to grab the 4,610th value in this list. If you Google find value by index from tensor in TensorFlow, then it's going to give you the method or the function tf.gather, where you pass in the products and you pass in the indexes, which is random negatives indexes. And you can see that we've now extracted 7 values from this list of products. And in case it's unclear what's happened here, if we just look at the list of products and I say, okay, give me the 4,610th value, it is in fact the same as the value that we see here. But again, the reason for using TensorFlow functions is because this is going to be optimized under the hood by TensorFlow and is going to take advantage of the architecture you have available. Okay. So we started off with a data set that just had users and products. And now we want to extend that to include not just users and products that the user purchased, but also these negative products that the user did not purchase. And the way we're going to use that is we're going to use a mapping function that's going to take in, sorry, if I just scroll back up again here, that's going to take in the user and the product and is going to spit out the user and the candidate values, both the product that the user purchased and the products that the user did not purchase. So we've got this mapping object just here. And so far, all this mapping object does is it takes in all the products that we can randomly sample from, and it takes in a value which we'll say is the number of negative products we want to take. But at the moment, this function does nothing. It takes in the user, it takes in the product, and it spits back out the user, it spits back out the product. So we really want to perform this negative lookup, the lookup of these negatives. So if we just copy and paste the code that we have from up here where we did the random sampling. So we're saying here that the random negative indexes, so we want how many negative products we want? Well, we want self dot number of negative products. And what is the list of values that we are sampling from? Well, it's the number of possible products, self dot num possible products. So this gives us a list of indexes of products that the user did not purchase. And so then we need to find those lists of products. So these are going to be the negative products that the user did not purchase. Negatives equals tf.gather. So that just means look up the set of possible products and find the find the products corresponding to the random negative indexes. So now we can create a complete list of candidate products, which are the concatenation of the products that the user actually purchased and the negative products that they did not purchase. And I'm afraid that there's a little bit of black magic just here, which is that I've previously done this, and I know that the axis, you have to specify an axis here. And the axis you need to specify is 0. So that's just how we're going to join these things. And actually, I see that I got an error here because you need to put these in square brackets because in principle, you could pass in a list of any number of tensors to join all together. So you need to specify a single list of tensors like that. Okay, so now we're going to return these candidates. Okay, so I don't like writing too much code before actually checking that the output looks correct. So if I copy, so let's copy this line right here, dataset equals tf.data.dataset from tensor slices. So this was just where we constructed our dataset from the list of users and the list of products. So I've copied that. I'm going to plonk that down here. And now I'm going to say dot map. And what's the function that's going to map? Well, I'm just going to construct my mapper class just here. And it takes in a list of the products, and it takes in a number, which is the number of negative products we want. I'm going to say 10. Okay. So now I can iterate through this thing just like I could iterate through things before. So I say for user and candidates in data set, print the user, and then print the candidates. And I'm not gonna iterate through the entire data set. Let's just look at the first row. So the first thing I get is the user, which we originally had. And the second thing I get is a list of products. That's 11 products in total. So that's the product that this user purchased and 10 products that the user did not purchase. So that's pretty cool. We need to do one more thing though. Our model is only going to learn if it's told which product the user purchased and which products the user did not purchase. So we need to pass it a y vector that says, yes, you want to predict a purchase for this first product, and no, you don't want to predict purchases for these final products. So in other words, we want a vector that's a 1 here, and then it's got 10 zeros. 1 showing a thing that we want to predict as a purchase, 0 showing things we don't want to predict as purchases. So TensorFlow has a function for doing this, and it's called tf.onehot. So onehot takes in a list of indexes. So I want to just have the 0 index being set to a value of 1, but I want a vector that's of length 11. So you have a look at this. So this is exactly what we're looking for. So this is a tensor where we've got a 1 at the start and then 10 more zeros. So this is going to be our y values. So just in my constructor, I'm going to create a y tensor, tf.onehot. I'm going to put the value of 1 right at the start. And then the length of this tensor has to be the number of negative products plus 1 to take account of the purchase product. So now I'm going to update my call function to say, okay, now return 2 things actually. First, return users and candidates. So I put those into brackets, and then return y. Okay, so let me enter that. So now let's update this this function where we call the data set. So the first thing I get out is I get out the user and the candidate products, and I also get out a value of y. So now if I also print y, I'll give you some time to catch up with that. We now get out 3 tensors. We still get out the user tensor. We still get out this list of candidate tensors, which is 1 positive product that the user purchased and 10 negative products that they didn't purchase. And then I get out a tensor that's just 1 corresponding to the purchase product and 0s corresponding to the non-purchase products. Okay, so we need to bring this all together into a single function so that we can just repeat all these steps for both the training data set and the test data set. So I'm going to go up to the top here, and I'm just going to copy and paste these 3 lines of code. So I'm copying the dummy user tensor, the product tensor, and the line that constructs the data set for those 2 tensors. And I'm going to paste them down here into this function here called getDataset. GetDataset is going to take in either the training data set, or it's going to take in the, either the training pandas data frame or the validation pandas data frame. So I need to make sure that I change the word train here to df. I need to change the word train here to df so that I can pass in whichever one I want. I need to line up my code just here. Okay, so now I've got dummy user tensor is just a constant of whatever data frame I've passed in. Grab the dummy user IDs values. My product tensor is the product IDs from that data frame, and then I combine them into a TensorFlow data set using from tensor slices. Then I'm going to apply the map to that data set dot map, and I'm going to construct this mapper. And the mapper takes in the complete list of products and the number of negative products. Negative products. So let's actually just, in the constructor of this, in the definition of this function, let's pass in the products that we want to rank amongst and the number of negative products. And again, this is going to be a hyperparameter that we're going to experiment with, or we'll have the opportunity to experiment with later. So let's just double check that we've done, haven't made any mistakes here. So I'm going to say for open bracket, the user and the candidate values, close the bracket, and the y values in get dataset. I'll pass in the training data set. I'll pass in the products, and I will define the number of negative products as 40. Okay, let's just go for 4 because that'll be nice and easy. So let's print the user, print the candidate items, and print the y values. And then I'm going to break because I only want to print the first row. I don't want to print my entire data set. So I'll give you a second to catch up with that. If we look at that. Ooh. You see, I didn't write this function properly because this function doesn't actually return anything. I need to return the data set at the end. And in fact, I'm getting out 5 products. That's 1 positive product, and then we ask for 4 negative products, and that's what we're getting out here. One final thing to say, though, is that we want to pass out a data set. We don't want to just learn from 1 user at a time. We want to learn from a large number of users at each time. So I'm going to create a final line here, which is data set equals data set dot batch. So we're just going to bunch up a large number of users and a large number of possible products all together. Typically, people pick numbers that are powers of 2, and it's not really clear to me why they do that. I think there was probably historical reasons for that. I'm going to pick 1,024 just because that seems like a suitably large number. Okay, so what's happening now is that the output of this data set is giving me a list of 1,024 users, and then 1,024 sets of candidate products. For each user, I've got 1 positive product and then 4 negative products. And then I've got 1,024 of these y values here, which is a 1 and then 4 zeros. So here's the code for get dataset. I'll take questions now, and you can catch up writing if you want to. So somebody asks, how do you know if the user didn't purchase the product because they didn't like it or because it wasn't available on the platform yet, is there a timing specification somewhere? So in this first simple model, the answer is no. And in fact, it's even worse than you said, because we choose random products. Well, we could randomly pick a product that the user did in fact purchase. And so that introduces a bit of error. But on the whole, I think that the chance of that happening is quite small because we have a large number of products and a small number of random products to pick. And if a user didn't purchase a product, again, we don't know why they didn't like it, but we do know that they did like these products, the products that they did purchase. And so hopefully we will learn from our model a mapping of products that users like. But it's very difficult to know why a user didn't purchase it. Maybe they would love to have purchased it, but it just wasn't available in their size, or if maybe it was in red or something like that. So I agree that that does introduce an error, and we're just going to have to learn to live with that until we can experiment and complicate our model a bit more. So I think actually in that answer, I think I answered a few other questions. One person, Charlie, asks if you can still work in a CPU rather than a GPU. Is one better than the other? You absolutely can build and construct your models on CPUs. Another way of saying that might be just on your personal laptop rather than using a GPU. Using a GPU is supposed to be a bit faster. And if you are very careful about the way you write your code, that sometimes depending on how you write your code, actually running on GPU isn't that much faster. For this model, I think this model is so small that it actually doesn't make much difference. So if you're following along on your CPU, it doesn't make much difference. One person asks, how similar is this model to the actual model we use at ASOS? So I would say that this is kind of a simplified version of the model that we use at ASOS. And I'll discuss ways that we could complicate and extend this model to make it a bit more like the model we use at ASOS, or a bit more useful for whatever use case that you personally have. Okay. Okay, some of these questions are already pretty smart. One person is asking about cold start users and cold start products, which I don't think that I've mentioned so far. So you're definitely very informed about the problem set. So this user who asks, do you have a simple trick for cold start users and products? So by cold start products and cold start users, they mean a product that's never been purchased before, or a user who's never made any purchases before. How can we make recommendations for them? And in this specific method that we're using here, the answer is we can't. We're completely stuck. If a user hasn't purchased anything, if a product's never been purchased, we can't begin to make recommendations for it. In the production ASOS model, we also have a way of learning from the images and text descriptions of our products to try and inform the way of to try and inform the model so that it's able to learn from products even before they've been sold. But that's significantly beyond the scope of this course. It involves computer vision and natural language processing, and there was no way I could fit that into 3 hours. Yasser asks, how could we consider the availability of products, assuming some products are available in a defined period of time? So I'm going to answer that question in 2 different ways. So the first way is to say, when you're defining your randomly chosen products, if you want to complicate it a bit, you could say, well, I'm only going to choose from amongst products that were available on sale and in stock on the day that this user made this purchase, in which case you need maybe a bit more logic in your mapper function. And the other way I'm going to answer that question is to say, okay, well, so we've defined this model here and we've trained it. Now we've actually got to put it on the website. We need to actually sell some stuff. We don't want to recommend stuff that's just been sold out. And for that, we just apply a filter at runtime that quickly checks, are these products all in stock or not? Okay, so I'm going to move on. And we're now finally going to bring the model and the data set together in a way that can train the model. Okay, so first we need to define our model. So I think we called our model simple recommender, and we need to pass in the dummy users, and we need to pass in the products, and we need to choose a length of embedding. So I'm going to choose 15. I did a small amount of experimenting before this, and 15 seems to work okay for the data set we have. If you look up Google, there are about 100 different people, each specifying different rules of thumb for how long the embedding should be. In my experience, not much beats trial and error. So I would certainly encourage everyone to experiment with different lengths of embeddings before fixing on a particular value. Okay, so we'll call this this model our model. Okay. So before we can train our model, we need to compile the model, and there's going to be a lot of black magic that goes into this final or I guess penultimate line. So when we compile our model, we need to pass in a loss function, and a loss function is the thing that we're going to try and optimize. So we've said we're trying to optimize for predicting purchases. What we're really saying is we're trying to optimize the number of times when the score of the first product is the largest score from this list of products. And we've got a number of different options, and we've got to try and get one correct, and we've got to try and avoid making any mistakes. So the loss function that we use for this is called categorical cross entropy. And so I'm just going to ask Keras to give us the loss function, which is called categorical cross entropy. Now, categorical cross entropy, you may have learned about if you've done machine learning in the past. We typically think of two forms of machine learning, regression and classification. Categorical cross entropy is used in classification. And so what we're now kind of turning this problem into is a classification problem where we try to classify the purchase product and versus the non-purchase products. A categorical cross entropy expects probabilities. It wants you to say, well, I think there's a 90% chance that this first product was purchased and a 3% chance the second product was purchased and so forth. But it has a way of converting scores into probabilities. And so when you create this categorical cross entropy, you need to use these words from logits equals true. And from logits just means I'm not going to give you probabilities, I'm going to give you actual scores, and you need to figure out the correct way of dealing with that. Okay. We need to define a second thing in this compile function, and that second thing is going to be called an optimizer. And you need to spell optimizer in the American way with a Z or a Z rather than with an S. So we said that the way our model learned was by looking at what it got right and looking at what it got wrong and going back to the embedding and making tweaks. Well, the optimizer is the thing that makes the tweaks. So you can kind of think of this problem as a way of saying, okay, let me figure out where I made mistakes and look in what direction I need to move my embedding values to try and make my mistakes, to make fewer mistakes and make the mistakes that I do make less egregious. So you're kind of looking at a slope and you want to try and find out what is the steepest slope so I can take a step in the direction of making, you know what, I've completely messed up that explanation. That was just embarrassing. Let me try that again. So we make a whole bunch of mistakes, we figure out what our errors are, and we then try to say, okay, what tweaks can we make to our embedding layer to try and make a smaller number of mistakes. And so for that, we need an optimizer that is called gradient descent. It's going to figure out what the right direction is to move, and then it's going to move downwards so that the loss is minimized. The number of errors that we make is as small as possible. So we're going to call tf.keras.optimizers. Again, optimizer spelled with a Z. And we're going to use one called SGD, which stands for stochastic gradient descent, and the GD there meaning that we're going to try and walk down this valley so that we try and minimize the loss, minimize the number of mistakes we make. It's going to figure out, hey, what is the direction that things are changing in the most so that I can make the best possible change possible to my embedding. But it still wants to know fundamentally, how big a step should I make? Should I make big changes when I go back and make tweaks, or should I make little changes? And so you can set a what's called a learning rate, and that tells you, okay, do you make big steps or small steps? Now, I personally have experimented and have found that a learning rate of 100 works quite well. But you can absolutely and probably should experiment with different learning rates. So the final thing we're going to write in this compile step is a list of metrics. So what are metrics? Well, we've already got this loss function, which is categorical cross entropy, which in some sense tells us how good a job we're doing of predicting purchases, where there are purchases, and of avoiding predicting purchases when a purchase was made. But it's going to give us a score that's not terribly interpretable and is a bit difficult to understand. Okay, so a big number is bad and a small number is good, but at a more base level, can we figure out, is our model actually learning anything useful? So we're going to create a metric which is not going to be used by the model to actually improve itself, but will be used by us to understand, is the model doing a good job or not? So we're going to pass in a list of metrics, but actually we're just going to pass in a single metric, but we need to pass in as a list because the compile function could in theory take in any number of metrics. And the metric we're going to take in is, so whereas the loss function we're using here is called categorical cross entropy, we really just want to know, are we correctly predicting purchases when we're predicting purchases? And so instead of categorical cross entropy, we're going to be using categorical accuracy. And so the way we access that is tf.keras.metrics.categorical accuracy, open bracket, close bracket. Okay. Okay, so if you followed this far, honestly, 10 points, well done. We're now at the stage of training our model. And the way we do that is we call model.fit. We need to create our training data set. So we're going to get data set. Get data set takes in the training data set, pandas data set, our data frame. Takes in a list of products, and it takes in a number of negative products, and I'm going to choose 100 negative products. We also want to pass in a validation data. So after we've trained our model and made some improvements, we want to know, hey, is our model actually just like memorizing the original data set we gave it, or is it actually useful in the real world? So we'll pass in some validation data, and that will be another data set, but this time it's going to be a data set using validation data. We're going to pass in the same list of products, and we're going to also rank from amongst 100 negative products. And the final thing we need to say is, okay, how many iterations do we want to do with this? So we're going to show all the data to our model. Model is going to make some changes. We can continue to get better if we continue to show, if we repeatedly show the data set to our model. And so the way we do that is we say epochs equals 5. That's just a way of saying repeat the fitting process 5 times. So if we do that, we're going to get a ginormous error. I'm not going to lie to you. Some of the times in TensorFlow, these errors are very hard to understand. But just at the bottom here, we can see that it's saying the problem is that our shapes are slightly mismatched. So this is saying none versus 101, whereas this is saying none 1 101. So what on earth could be the source of that problem? So here is our data set that we're passing in, and we can see that our y values are tensor of shape. Okay, 1024, that was the size of the batch, and by 5, that was the number of negative products plus 1. But if we look at the output of our model, if we scroll up to the example we did of that, just here, we see that our model is outputting, okay, so we gave it 2 users, so that's the 2 here, and we gave it 3 products each time, and so that's the 3 here, but it's created a new dimension here. Why did it do that? I don't know. And actually, in my experimentation, I found that it doesn't do this when you're on CPU, and it does do this when you're on GPU. So this is why you just need to be very calm and very careful about what it is you're doing. So I'm afraid the solution to this is we need to change our model just a little bit. And the way we do that is we want to try and delete one of the dimensions. We want to try and delete this, this kind of middle dimension right here. And the code we use to do that is tf.squeeze. If you just look up remove dimension from TensorFlow tensor, then you'll get back you should use this function squeeze, So you take in your input and then you say which axis is it you want to remove, and we want to remove that middle axis. So not the 0 axis or the number 2 axis, we want to remove axis number 1. Okay, so if I now create a model, dummy users, products, arbitrarily call that model. So I get the same output, but I basically just lost a set of square brackets. So how annoying was that? Really quite annoying. Okay, so I've now fixed, let me show this code just for another second. We'll go back and train this model. So I went back up to the definition of my model, and I just wrote squeeze here because for whatever reason, TensorFlow in its ineffable wisdom has introduced an extra dimension that we do not want. So that's debugging in TensorFlow. How about that? Okay, so let's go back down. So we're going to reconstruct our model, compile it again, and fit it. And so now we've got something that's actually doing something. So we're passing through our data, and we've got this loss, and we've got this categorical accuracy. So this is the accuracy in our training data set. And then we've got some validation data, and we're seeing here that we're actually getting 1%, actually 4% accuracy. Now we have 100 random negative products. So if we were just choosing randomly, we would get the correct answer just less than 1% of the time. And so what this categorical accuracy is telling us here, giving us a value of 10%, is that it's getting it right 10% of the time, not 1% of the time. So this is telling us that our model really has learned something, and we can use this model in order to produce recommendations. So this is really exciting, and this is exactly what you're looking for. You yourselves might want to experiment later on by trying a different embedding size, different learning rates, different number of negative products, and easiest thing to do is just to whack up to a really large number of epochs and see, hey, does your model continue to get better, or after some time, does the improvement does it stop improving? I'm going to show one last thing in the code, and then I'll take some questions before handing over to my colleague Neha. So there was a little bit of code in the model that I didn't talk about. So let's have a look at that. So I said that so what we built here is a way of personalizing recommendations. We're able to take user vectors and we're able to take product vectors, combine them, and create scores that we can use to rank products. But out of this, we get out a little bit more information. We also figure out what products are similar to each other. So what we can do is we can take the user vectors and we can take the product vectors and we can throw away the user vectors. And then we can take the product vectors and we can say, okay, here I'm looking at a specific product. So I find the vector of a specific product. And then I can take the dot product with all my other products to find out which products are most similar to that first product. And when I do that, I get back a list of similar products that I can put on my website as a list of products called you might also like. So you're looking at a pair of shoes, it's good. It's not exactly what you're looking for. So we show you another list of products to go alongside it. So that's the code that I've written just here. So I'll talk you through it. So this is a function called call item item, meaning find item to item similarity, find products that are similar to this product you pass in. So you pass in this product, and first of all, we need to look up the product table to figure out, okay, so which embedding corresponds to this product ID. And then we need to go and grab the embedding. So then we look up the embedding just here. And as you can see, things get very complicated with shapes and dimensions. And so by trial and error, I figured out I need to make sure that this thing is the right shape. And then I can take all the embeddings for all the products and grab them just here. And okay, again, do some clever stuff with the shaping. And then I take the dot product. So what I'm doing here is I'm taking the dot product between the product embedding for the product I want recommendations for and the product embedding for all the other products. And finally, what I do in these last two lines is I say, okay, just give me the scores for the 100 highest scoring products. This returns both the scores and the indexes. And then I figure out, okay, these indexes correspond to which products. I grab those products. And so then I'm going to return the product IDs and the scores. Later on, my colleague Nihal will talk about this little decorator called TF function, I don't want to step on our toes, but essentially, when we come to productionize a model, any model you want to call as an API, you need to decorate with this little TF function. Okay, so this is a bit of code for finding item-to-item similarity. Okay, so we've trained our model, we defined our model, we trained our model. It was a lot of effort, but now we're in a position to say, okay, so our model claims that it's getting 11% accuracy, but is it really doing a good job? Well, here is a product, and so we can ask, okay, give me products that are similar to it. And so it gives out this list of products. So let's look at this product just here. So if we go to, if I copy this product ID, I go to asos.com/PRD for product description, PRD / and then I paste in this product ID. Okay, so this product that we're going to make, you might also like recommendations for, is this Pull and Bear Snoop Dogg t-shirt in black. So you see that the data set that I pulled is actually a bit out of date and it contains some out of stock products. But no matter, we can still produce recommendations. In fact, if anything, recommendations are more important on this page than they are on other pages, because a user comes to an out of stock page and they must be frustrated by that. You might also like recommendations are really important. So what is the highest ranked, highest scoring product, the most similar product to this that we have found? So I've copied this first index. I go to asos.com/PRD/ and then I paste in that, that product ID. Okay, so I started off with this kind of big black baggy t-shirt, and now I'm recommending this t-shirt, which is also kind of a bit big and baggy. So I guess I think, hey, that's a pretty good recommendation. Well, maybe that was just by chance. So let's look at this second recommendation, asos.com/PRD/ and we'll paste in there. Okay, so this Tommy Hilfiger slim fit suit jacket. Would you wear this jacket with this t-shirt? Well, I guess I'm not quite so sure about that one. But the point is that these recommendations are maybe not totally insane, and that with a bit more effort and a bit more time, and with a bit of experimentation in terms of the size of the embeddings, the learning rate, and the number of negative products, as well as the number of epochs, you can see that you might be able to train a model to get a model that's pretty good. So I'll answer some questions in a second, but somebody asked earlier, how does this differ from the ASOS production model? So one way it differs is we say, well, for products that have never been purchased before, we're going to learn from the images and text descriptions of those products to try and figure out which products are similar and which products are good for each user, are an ideal recommendation for each user. Another way is that we say, actually, you know what, it doesn't really make sense to learn these embeddings for our users, because we only know, the only thing we know about our users is the products that they've purchased on our website. So instead of creating a embedding for every user, and we've got 23 million users, instead what we'll do is we'll say a user is the sum of the products that they've purchased in the past. So we'll say, hey, Gordon purchased these 9 products. We'll go and find the product embeddings for those 9 products, and then we'll take an average of those, and that now defines Gordon's user embedding. And then we take dot products, and then we create recommendations. And so this actually improves the model in performance, because now the product vectors also, in some sense, capture the style of the users who purchase them. And it also makes the model much more tractable, because instead of having 23 million user vectors, you don't have any user vectors, you just have product vectors. Okay, so let me take some questions. So one person asks, at ASOS, do you also make recommendations simply based on the similarity of features of 2 products? So if by features you mean like actually the descriptions of these products, then the answer is yes. When we don't have access to other data, when a product hasn't been purchased before, then we learn from the images and the text descriptions of the products to try and find out products that are similar to one another. But the moment we start getting user insight, when users actually start purchasing us, we've purchasing our products, we find that that is much more powerful in terms of telling us what products are similar to one another. So that's what we do instead. Zana Meliva asks, what categorical accuracy is considered as good for a recommender system? The problem is that the value of categorical accuracy you get is going to depend on how many products you have to choose between. In this data set we have here, I think there's about 30,000 products. But on the ASOS website, we've got many tens of thousands of products that are in stock today. And over the course of the last year or so, we've had hundreds of thousands of products that have come onto the site and sold out. And so different levels of accuracy the level of accuracy that's good will depend on the level of accuracy, will depend on the number of products you're choosing between. But as an example, a few months ago, I was able to improve our model slightly by increasing accuracy by 7%, and 7% was enough to be able to see an improvement on the website, to be able to see that users actually felt those new sets of recommendations were measurably better. Okay, yeah, somebody asks if I can show the model definition for a second. So hopefully this is, and the compile step. I realized that there was a lot of code in this compile step. So hopefully you've had a chance to look at that. And I'll scroll back up to the model in just a second. So one person asks about, could this approach be extended to produce outfit combinations? Can products, instead of saying, well, okay, you're looking at this pair of shoes, it's not exactly what you're looking for, let's look at some other pairs of shoes, could we actually say, hey, you're looking at this great dress, here's the shoes that go with that dress? And the answer is yes, and that is something that is a problem that ASOS and some of my colleagues have been working on. We take a broadly similar approach. We still have product embeddings, but in this case, we're not just trying to look at single products that were purchased. We're trying to look at products that go together. And there are two kind of ways you can approach this. You could look at sets of products that users have purchased at the same time, or you can look at the approach that we've taken so far is to say that when we photograph our models wearing t-shirts, they're photographed wearing an entire outfit. And so we can actually say, we can pull the information out of this image and say, okay, well, what products was paired together by the stylists at ASOS? What products do they think goes together? And with the training embeddings, we can try and figure out what products go together in a more general sense. Is there any value in increasing the depth complexity of the model by adding more layers for a problem like this? So there was a really interesting paper at the Recommender Systems conference 2 months ago, which talked about this. One of the interesting things, though, is that although you can create a large number of layers to eventually create a single output instead of using the dot product, actually what this paper showed, and this paper was by some people at Google, they found that actually trying to create layers that actually do better than a dot product was really difficult. And in fact, they weren't able to do it. And they said, okay, well, maybe if we put in enough layers, eventually we'll be able to do something that beats just 2 values in a dot product. But so far, it's a bit of a struggle to do that. So actually, this model, although simple, is spectacularly powerful. One person asks, can you describe the difference between the test data and validation data and the training data? And I think that'll be the last question I answer before handing over to Neha. But it's a spectacularly good question. And the answer is that it has to be slightly different to the approach to splitting data that you might take in other machine learning contexts. So in another machine learning context, you're building, say, a model that can predict whether a photograph shows you a cat or a dog. There you want to make sure that the test set and the training set are very similar to each other, because when you improve on the training set, you want to make sure that that corresponds to an improvement on the test set, and that the test set data represents the real data that you might actually interact with. For recommendations, it's slightly different. It's always going to be the case that you learn from one set of data historically, and then you apply that model. In production. So there's a temporal difference there, and the temporal difference is really important. If you're making a movie recommender, if in your training data set you don't think of splitting by time as important, and your training data has movies that you watched later and your test data set has movies that you watched earlier, then if in your training set the second Harry Potter movie appears, well, okay, it doesn't take a genius to predict the first Harry Potter movie is something that you might have watched. Whereas if both the first and the second Harry Potter movie are in your test set, as in those were things that you're trying to predict later on, well, actually predicting that you watch either of those might be a bit more challenging. So when you split your training data set and your validation data set, and indeed your test data set, you need to make sure that you do a temporal split, so that, for example, you take 6 days worth of data in your training set and then 1 day of data in your test set. So I hope that that answered that question. I do see that there are more questions to answer, and I'm sorry I wasn't able to answer all of them in person. I will type answers to some of these questions going forward, but right now I'm going to hand over to my colleague Neha. So far we've built a machine learning model that works in my notebook, but how do I actually get this to real users? So I'm going to hand over to Neha.
Thank you very much, Gordon, for the wonderful session. I certainly learned how to train recommender model today. I hope you all have enjoyed it too. I'm waiting for my screen to share. I hope you can see my screen.
Yeah, looks good to go, Neha.
Oh, can you see ASOS webpage I'm showing?
Yeah, I can.
Thank you. Okay, so as with Gordon, we have seen how we can build model in Colab notebook. But what's next? What can we do with the model we have in a notebook? When we browse product page on ASOS website or mobile app, we see product recommendations. These are powered by powerful recommender model we have in production. I'm just waiting for this to show up. So web page, the ASOS web page we have seen earlier, it doesn't call function from a notebook. We have deployed an endpoint in production. Web page calls an endpoint. It executes item function, which we have seen earlier, which returns list of recommendations. Those recommendations appear in a carousel on a page. First recommendation, first product appear first in a list, second, third, and so on. In production, we have deployed endpoint using TensorFlow Serving. It exposes an endpoint for a web page to call. It supports volume of traffic we have on ASOS website. We see customer interactions with products changing rapidly. Model learns from rapidly changing customer interaction. We train recommender model daily. TensorFlow Serving detects and loads new model automatically, which allows us to provide good shopping experience to our customers. TensorFlow Serving also allows us to set up tests for new models. We constantly test new propositions to make customer experience better and better. And so we have endpoint deployed in production using TensorFlow Serving, as TensorFlow Serving meets all the needs we have. I have hands-on session.
Yeah, can I just get you to share the full presentation, because we can actually we can only just see your sidebar as well. If you go into the presenter mode.
Can you see full presentation now?
Yep, that looks perfect. Do you want to just
Yeah. Sorry.
brilliant.
Yeah.
Great. Thank you so much. Thanks.
Oh,
no, you're back. You're back to them. There you go.
yeah. Sorry, it's my internet seems slow.
No worries. Thank you.
Yep. Here is where we are. So just to repeat, on when we see product on web page, it doesn't actually execute function from a notebook. What we have is an endpoint using endpoint we have deployed using TensorFlow Serving in production. Why? Because TensorFlow Serving meets all the needs we have. It exposes an endpoint for a web page to call. It supports volume of traffic we have on ASOS website. We train model recommender model daily. TensorFlow Serving detects and loads new model automatically, which allows us to provide good shopping experience to our customers. TensorFlow Serving also allows us to set up tests for new models. We constantly test new propositions to make customer experience better and better. And hence, we have used TensorFlow Serving in production to deploy this recommendations endpoint. I have a hands-on session for you where we together set up endpoint for recommender model we have built in Colab notebook with Gordon using TensorFlow Serving on our local machine.
Neha, your slide is getting cropped off on the right-hand side. Can you just check if you can?
Is this fine?
Yeah, that screen is being cut. The one with the recommendations. The one after seems okay.
Okay.
Do you want to just click through a few, Neha, just so we can check? It might be a PowerPoint setting.
Yep.
No, it's still cutting off for me.
Right side, left side?
The right-hand side.
Right-hand side. It's how much can you see? Can you see this image? Can you see the image?
Yeah.
Yeah, the image is fine. It's the text on the right is getting cut off on the right-hand side.
Okay. So trouble is, I think I'm using web browser, so maybe that's why. It's still fine. The point we can go ahead. The point I was making is how that how web page how in production we have API endpoint which gives us recommendations which gets displayed on a web page. Can you see this slide fine? Can you see the text in this slide?
Yeah.
Okay. Yeah. And I was explaining in previous slide, I was explaining why we use TensorFlow Serving as it is a powerful powerful system for machine learning models. So what I was saying is what we are going to look at in this session is how we can set up TensorFlow Serving API over model we have built earlier in a session. Setting up TensorFlow Serving is very easy. All we will be doing is we will be saving recommender model we have in Colab notebook on our local disk. I will show you how we can save a recommender model. We are going to download that model locally and then run TensorFlow Serving in using Docker image on our local machine, and that's it. We have endpoint over recommender model. For during setup, as we go along, setting TensorFlow Serving up, we will be following commands from a GitHub repo. I hope you all can see the section I'm showing. We will be using Docker image from Docker Hub. Image contains set of instruction for setting up endpoint using TensorFlow Serving. When we run an image, it sets itself up as isolated online system on any machine, Windows, Mac, Cloud VM, or cluster. So whether you have Windows machine or whether you have Mac machine, you will be able to set up TensorFlow Serving over model we have built in Notebook. We do not need any additional installation like Python interpreter or Python web server in order to set up an endpoint. You will see later in a session that even we are not writing any Python API code in order to deploy API over recommender model. It works on Windows and Mac machine, and whether you are on Windows machine or whether you are on Mac machine, you will be able to set it up. I stress out it's useful to know how to set it up locally. You then can use the same image to deploy API at scale in production, which is what we have. We have deployed API at scale in production on cloud. However, it is not it is not in scope of this session where I will take you through how we can deploy API at scale in production on cloud. I will be adding instructions on a GitHub repo later whenever I can. You can then try it out yourself in your own time. In this session, what we will be looking at it is how we can set up TensorFlow Serving on our local machine. We have sent out instructions earlier where we have asked you to have Docker engine install and some HTTP REST client install for you to be able to follow this session. So yeah, let's get started. It's fine if you haven't the people who have built recommender model with Gordon. They can follow the session I'm going to show where we will be saving the model. If you haven't managed to reach up till this point, it's fine. We have uploaded a model artifact which we will be saving soon on a GitHub repo. If you want to try setting up TensorFlow Serving on your machine, please, you can go ahead and download this model on your local machine. So yeah, you will be able to follow rest of our session. Can you see my Jupyter Notebook fine? Is it cutting off or is it fine?
It's still cutting off on the right-hand side.
Is it here? Okay, I think I may be able to. Is it better now?
Yeah, it might be that you can reset the sharing of your screen to full desktop. You might have selected part of it through cropping.
Oh, I see. Yeah, shall I try it again? Okay, yeah, sure.
Yeah, maybe try sharing the whole screen instead of the browser.
I did say entire screen. Okay, let me try again. What can you see now? Can you see me browser moving? Can you see browser?
Yeah, it's still cropped, unfortunately. I'm trying to think of anything we can do at our end.
I'm definitely sharing entire screen, so that should be fine. How about this window? What can you see on this window? Can you see entire window or not?
No, again, it's still being cropped on the right-hand side, but about a quarter of it.
Okay, what I can do is
there's a couple options. I mean, you can minimize the screen to make it half size,
yes,
or
yeah,
we can reshape the window so it fits in the viewing window.
yeah, sure. Okay, I'm trying something different. Okay, can you see full screen now, or is it still cropped?
Yeah, that looks great.
Okay, sure. Maybe okay. I'm using another monitor, and that may be why it didn't work. Yep. So sorry about for a little hiccup. So yeah, let's go. So as I've mentioned, what we need to do is we will save a model we have in Colab notebook. It's fine if you didn't manage to follow all along. I have a model artifact for you on a GitHub repo. So you model artifact for you on a same GitHub repo. So you can download this model artifact and then we can see TensorFlow serving setup on our local machine. For those who are following with me, I'm showing how we can save model on Colab notebook and then we can have it downloaded on our local machine. You can which will be helpful for you to give it a try on your own time. We are following save the model session now. For saving the model, we need to specify the path where we are going to save a model. This path should follow a convention. We specify base directory, we specify name of the model and version number. So in production, we train a model daily and training script saves a version of a model daily. So I'm going to run this cell. Then we specify the shape of the input function is going to accept. Just a reminder, when we have built simple recommender model, Gordon has shown us item methods that item functions, which gives us product, which returns us product recommendations. What we would like to do is we would like to expose item function over API so that then web page can call API and call API endpoint and execute item function, which then gives us recommendations and that those recommendations appear here. So we know that item function, which gives us product similarity, accepts product ID, which is an integer. So we define shape of integer here. And then when we save a model, we also have to say which function we would like to save. We would like to expose when we save a model. And hence we are going to say we would like to expose item function. That becomes our signature. So now let's try. Let's save the model. For that, we will use save model method from TensorFlow. So we are going to execute save. We are going to call save method, specifying model we would like to save, specifying path where we would like to save the model, and signature we would like to expose. And we done a save. Yep. So it says that it has saved model here. In your collab notebook, when we refresh, if you are following along, when you refresh, you should see folder being created. We have saved recommender model, and then you can see the artifacts here. These are TensorFlow Serving compatible artifact in protobuf file. I'm not going into much detail about the format of this file at the moment. It's enough for you to, it may be sufficient, to mention here that this function gets saved as a graph in this protobuf file. If we have time, we will come back to it, and we can discuss more about this. So we have a model artifact in our collab notebook. Let's quickly check if model is saved fine or not. So I have a cell here which I'm going to run in Jupyter Notebook, which can tell me if model is saved fine or not. We can once we have saved model artifact, we can still continue using Python, and in Python, in Notebook, we can quickly check if model is saved fine or not. So here, what we can see that model got loaded fine, and then it has exposed this item function, which returns list of recommendations, which is what we want. I have a cell here, which using which we can see how whether save model how save model is performing, and whether it is returning recommendations as we are as expected. So let me grab a product from a website here. I'm going to specify that product as an input. I'm invoking item function, which gives us product recommendations, and I have a little code here which shows product images for product in question. Product images for recommendations, it has written, item function has written for this product. And yeah, there we go. We can see that model has saved fine, and when we set up TensorFlow serving, we will be able to call item function from API. Okay, so okay, I'm going to pause here and quickly check questions if you have any. Uh, okay, yeah, it looks like there are no questions at this point. Okay, so I'm going to continue. Sorry. Okay. So here we are in a collab notebook, and we have saved model here. Let's download this model locally. We again on the same notebook, I have a code there which zip this folder, which will zip this folder, and we will then download this zip folder. It is the same folder which you can see on GitHub repo. So as I'm downloading model from collab notebook, you can download model from GitHub repo for us to then follow along next session, next part together. So yeah, I'm going to make few tweaks here, which I've spotted yesterday. Yeah. Okay, I have a zip folder here, and from I'm going to use Colab notebook feature, download feature to download model on my local disk. Yeah. Okay. So I have a model on my local disk. I'm going to save this model under C demo folder. I have a Windows machine. For Mac users, uh, I advise to save this model in a shortest possible path. We have seen sometimes that if you save model deep inside directories, then you may have trouble when we you it may not work smoothly for you when we go to commands section. Yeah. So I advise you to save a model at a root directory. Let's unzip the model, and after unzipping, we should see the same output we have seen in a Colab notebook. So we should have parents model folder, we should have recommender model, and model artifacts within version number. Yeah. So here we have parent model folder, we have recommender model folder, and then model artifacts inside version model. Okay. I hope you managed to catch me this far. Let's jump on to our command windows to now set up TensorFlow serving. Just a reminder, as I've mentioned earlier, we will be following this section from GitHub repo. We will be using Docker commands to set up TensorFlow serving on our Docker machine. I have added commands for Windows and Mac, both commands for both Windows and Mac, and uh, hopefully following these commands, you will be able to set up TensorFlow serving fine on your machine. So yeah, let's see. I'm going to run command 1, which is where we are going to switch directory cd to directory where we have saved our model. However, all the way up to where we have saved version of a model. So you should be in a right directory. You should be in a directory where we have saved version 1 of a model. Now, next, we will be pulling down Docker image, TensorFlow serving Docker image using Docker pull command. When we work with Docker, we use Docker commands. Docker pull is one of the command which we use to pull down Docker image. Once again, this Docker image contains set of instructions which allows us to set up API over our recommender model. It sets itself up. We do not need any other instruction, any other installation, installation. It works on Windows and Mac machine fine. So yeah, if you are using Windows machine or you are using Mac machine, you should be able to set up TensorFlow serving over model fine. Let's run this. So this pulls down an image. hopefully you can quickly check using Docker images command that it has pulled down whether it has pulled down an image or not, and then and we can see here that it has pulled down image on a Docker machine. We are now on a command 3 where we are going to run this Docker image. Windows user can use this version of a command. Mac user can use this version of a command. I'm just clearing my screen so that you can see the command fine. Okay, so we are going to use Docker run command to have TensorFlow serving up and running over recommender model we have downloaded earlier. When we run a command, we specify a port number. This is the number where TensorFlow serving exposes HTTP endpoint, and we are mapping it to a same port on our local machine so that later on we can use this port number to call an endpoint. Then we specify a path where we have saved the model. First section of path is important. Here in first section, we specify our local folder path, and then we map it to model name folder on Docker container. Then we specify name of a model. We will use this name of a model when we make a call to item method. And last, we specify image. Let's run the command. Yeah. If you see this long alphanumeric string, it means that it has run successfully. We can check whether it is up and running using Docker ps command. Yeah, and here we can see that it has created and it is up for 7 seconds. How we can check whether TensorFlow serving is set up fine or not is using Docker logs command. So we say Docker logs, and then we specify this ID of a container to check the logs for this specific application. Yeah, and you should expect this standard log. We can see in a log that it has successfully exposed this REST endpoint at localhost 8501 port, and this is the endpoint we will be using to make a call to get recommendations by calling item functions. I'm pausing here. I'm pausing here to see if you have any questions. Okay, Alex, we will go back to model saving instructions later once I'm finished showing. Is there a way to deploy shadow releases with TensorFlow serving comparing a model versus the new model simultaneously in production? Okay, yeah. Okay, I will answer these questions later. Okay, so from the log we can oh sorry, I've lost the screen. Okay, from the log we can see that TensorFlow serving is set up fine, and it has exposed endpoint at localhost 8501 address. I have a command. Here where we can call, using which we can call an endpoint. Mac users can use curl command to call item method, providing product ID, and you will see a list of recommendations getting returned. Windows users can continue using PowerShell and can follow this command, and hopefully you should also see recommendations written. I have created a test page, demo page here, which I'm going to use to show you that API has set up fine and how we can call item function over recommender model we have saved earlier. So once we set up TensorFlow serving, it gives us this endpoint. TensorFlow serving uh, provides us this base URL. We specify name of a model, and here we are calling its predict endpoint. When we have saved a model in Colab notebook, it has given us this predict endpoint. We next specify the body of a input. When web page calls an endpoint, it makes a REST request. The body of a request is in JSON form. As we can recollect, we have exposed item function. So here we are going to say, when we make a call to predict endpoint, call item method. We specify item method as a signature name, and we specify product ID as a input. And there we can see the endpoint we have set up locally gives us list of recommendations, and we can see, and here I'm showing the images for these products, for this product. So yeah, hopefully most of you will be able to follow this session with me. And if you have managed to follow, then once you have run these curl command and rest client on Windows machine, curl command on Mac machine, and Windows and rest command on Windows machine, you should have seen this list of products here, list of recommendations getting written. In production, so what we have done is we have set up TensorFlow serving in local machine. However, in production, we have deployed TensorFlow serving at scale in cloud. We have used the similar approach. We have continued using Docker image. We have used similar approach. We have continued using Docker image. We have deployed API endpoint at scale in production using Docker image. So that's why it's useful to know how to set up TensorFlow serving, and you have seen how easy it is to set up API over model you are building. You need not to write any Python API code. You if any of you, if some of you may have heard of engineers mentioning Flask application, writing Flask application, writing Python API, running it on Python web server. You need not to do any of it. Once you have a model, you can we save a model following specific convention, and then we set up TensorFlow serving, attaching model we have saved, and there we have REST endpoint readily available for any web client to use. It can be integrated on web page. It can be integrated on mobile app. It is very easy to set up API over TensorFlow model. TensorFlow serving is high performance online system for machine learning models. We are using it in production. We have deployed it in production at scale, and that's why we propose TensorFlow serving in this session. I'm going to pause here and ask some of the questions we have here. Okay, yeah, Alex asked if we can go over saving saving part again. Sorry, I don't know. Sorry, I don't know why I keep opening that window. Oh, it's not this one. It's this one. Yeah. Okay. Yeah. Here. Yeah. Here we are. So Alex, for your reference, for in order to save a model, what we need to know is which function we would like to expose. In our case, we have built recommender model. We have it has item function. It returns product recommendations similar to this, and we would like, when we save a model, we would like to expose that item function, so that when we deploy an API and call that function, it gives us recommend product recommendations. We When we save a model, we need to know shape of the input function can accept. In our in When we have built recommender model and item function, we know that it accepts integer product ID, which is an integer. So we define model path. Model path should follow a convention where we specify base directory, name of a model, and version of a model. We specify shape and type of input. We specify which function we would like to expose as a we would like to expose when we save a model, and then we, using TensorFlow save model save method, we save a model which gives us saved model in a saved model format, which is TensorFlow compatible format. So I hope it has answered your question. On Mac, yes, on Mac with download zip error missing name input. Yes, yeah. DA, sorry, I cannot see your name here, but yes, I have noticed it. Going back to how you can save model on Colab notebook you have been building. I have noticed few changes we will make, and we will upload the version which we can later try. inputs object. Yeah. So hopefully once we push changes, you will be DOM. Once we push changes, you will be able to uh, you will be able to run it in your collab notebook. Is this deployment implementation scalable? Yes, yes. This it is from Conrad. Yes, this deployment implementation is definitely scalable. Let me share. Prepared. I have prepared one slide to show you all how it has been deployed in production. Let me see if I can quickly show it. Can you see the slide fine? Can you see the presentation
That's
fine?
fine.
Yeah.
Okay. Okay. Yeah. Oh, sorry. Sorry, it's taking a little bit time. I need to. Yeah. Here we are. So in production, we have deployed API at scale, which is what this web page is using is calling. We have deployed API on Azure AKS cluster. We work with Azure Cloud. We have deployed API on cloud. We have deployed API using Docker image. We have deployed API on AKS cluster. When we deploy API at scale, we deploy it over multiple nodes to match the traffic we have on our ASOS website. So hopefully that should have answered your question. Okay, I'm going back to chat window. Yes, Charlie. Charlie's question is, how do you scale the container on cloud? Do you use Kubernetes? Yes, yes. We use Kubernetes in Azure. We work with Azure Cloud, and we have deployed API on Kubernetes cluster in cloud. Is there a way to deploy shadow releases with TensorFlow Serving, comparing model versus model simultaneously in production? It's a good question. Yeah, I would like to answer this question. I'm answering this question. Can you see my local machine folder? Fine.
Yep.
Okay. Yeah. So what we can do is TensorFlow Serving also supports side-by-side deployment of a model. What we have done is what we have set up is how we can have API over single model, and hence when we have set up this API locally, we have been very specific about a model name. However, what can also be done is TensorFlow Serving allows us to set up models side by side. In that case, in that scenario, we will use configuration file. So instead of mounting a single model folder, what we can mount is a folder parent folder which can have multiple models. We specify uh, name of a model in configuration, and then we mount this parent folder when we set up TensorFlow Serving. So this will allow you to have multiple models set up in production. You can um, as per your best as per your design, yeah, you can use this functionality for shadow model versioning deployment. I would like to show one more functionality, functionality which you can use in production. As I have mentioned, we train model every day in order to give continue in order to continue giving best customer experience. Model learns in production every day, new customer interactions, and we train model every day. So we keep this this carousel as recent. Um, we keep this carousel recent based on customer activity. Since how TensorFlow knows how TensorFlow helps us here. TensorFlow serving automatically detects can automatically detects new version of model is easily. So when we train new model and put it and add new version of a model here, it automatically serves the new model. So you can try in Jupyter Notebook, you can try saving a new version of a model, and then you will see that TensorFlow Serving has automatically load the model. Let me show you this part. So here we are saving a new version of a model. I'm running this cell. We are defining the signature, and this save should give us a new version of a model. Okay, let me zip this up. Okay, hopefully it should have given me the latest one. Okay, let me try deleting this in case it doesn't give me the latest one. And here I am downloading. Oh, okay, it is taking some time. Okay, by that time, okay, let me. Okay, I will try answer some other questions. Yeah, we will upload the notebook. Type. Yes, final code will be available where you can learn and get understand more about. Yeah. Marty, yeah, we will share some uh, official documentation link which you can go and refer. Yes, Shankar, good call. In order for, okay, let's go back to a collab notebook. Shankar's question is, can you brief how that decorator TF function need to expose the call item. Okay, let's go back to collab. Let's go back to notebook. Yeah, one thing you have noticed, sorry for scrolling. Yeah, one thing you have noticed is when you have defined model with Gordon, as you are following Gordon, as we have said, we would like to expose this item function. TF, when we try save model using TensorFlow save model save method, it will not work without this decorator. This method should be decorated with TF function in order for in order for this function to be saved as a graph. here. So with that, I hope I have answered your question. Okay, Luis, after Docker run command, I see my container is running logs. Show the model is loaded. Missing name input. Missing input product ID. Yes, yeah, Luis. Yes, we will. I will rectify this. I will upload the change, and then you should be able to see TensorFlow serving setup fine for this model you are building with Gordon. Yeah, I think, yeah, those are the questions. Okay, so final bit, as we were downloading the model, I will quickly show if and now okay, how in production train model, how in production TensorFlow serving can detect trained model every day, and how we can quickly, how it helps us quickly refresh the model. I'm just checking if this has, oh, perfect. So this is the folder I was looking for. Okay, I do not need this. Let's check. So in this folder, I have models. I have parent folder. I have recommended model, and then two versions of a model. Maybe so. Okay, I messed it up. What you should have seen it happening is, as soon as, yeah, okay, sorry, I was playing around with the folder we have attached. In reality, what should have happened is we keep creating new version of a model in a same location, and then in log you will see that it has successfully loaded this new version of a model, and then successfully saved this version of a it has a successfully loaded new version of our model, and we have then recent recommendations served from that version of a model. How can you check if model how can you check model metadata is through another TensorFlow serving endpoint, which I have mentioned here. So yeah, I've mentioned, I have put all useful API endpoint details in a GitHub page, which you can go have a look at it, have a look in your own time. Yeah, so we that's all I have to go through with you today.
Great, thanks Neha, and thanks to Gordon as well. I don't know if Gordon's able to pop back online briefly. If you've got any more questions that have come up later on, perhaps you can put them into the Slack channel. We might be able to follow up some of them later. But really like to thank Gordon and Neha for a really excellent presentation. I know a lot of people have been asking to have sight of the workbook that Gordon was working on earlier, so I'm sure they'll just update the link that's accessible through GitHub, just so that the final version's there for people to see. Thanks again for ASOS, not only providing the speakers this morning, but being one of the sponsors who keeps these sessions free, along with Data Idols, Facebook, Depop, Gusto, Deliveroo, Data IQ, and Royal Mail. If anyone wants to see the video again, please look in the chat session. We've got the links there. You can either upgrade your ticket or share a link on social media, and we get an access code for free. Just like to remind you that there are some other sessions coming up in the Data Science Festival that I'm sure you'll really be interested in attending. And And thanks to the attendees for coming and asking some really great questions about this. But I'd just like to end with a sort of virtual round of applause for Neha and Gordon for their really interesting session this morning. So thanks very much.
Perfect. Thanks so much. I don't know, Gordon, Neha, did you guys enjoy the session? Was it different doing it virtually? I'm assuming you normally do this with a much smaller group.
Yeah, I certainly enjoyed it a great deal. I found a question answering a bit difficult. I think that might have been a bit more, we could have been a bit more interactive next time in a post-COVID world. But yeah, I had a great time. Thank you.
Perfect. Thank you guys so much. And everyone, I'll be on the Slack channel, for half hour after this. So if you guys want to swap any ideas or anything like that, or be able to help each other, definitely jump on that. And hopefully we'll see you guys soon. So Charles, Gordon, Neha, thank you guys so much. Have a great rest of your Saturday and see everybody on Monday. Thanks very much, everyone.
Thank you very much.
Bye.
Bye. Have a lovely day.